Welcome to this manufacturer showcase hosted by NYSERDA's Empire Building Challenge. Its purpose is to familiarize you with new and emerging technologies meant to facilitate decarbonizing our building stock and applicable across entire portfolios. All sessions will be recorded and available upon request, and slide decks sent to all attendees. Each presentation will be 20 minutes, followed by 10 minutes in which the presenter will respond to your questions. We ask you to go on mute until then. And now it is my pleasure to introduce to you our presenter, Avideh Zakhor of Signetron. Avideh?
Hi, everyone. Thank you so much, Sal, for inviting me to give this talk. I'm going to be talking about high-resolution and accurate 3D building scan to BIM technology that Signetron has been developing over the last few years, and I will also talk about some of the applications of robots and drones to this problem as well. So what problem are we solving here? We are interested in recladding buildings with insulation panels to improve their energy efficiencies, and to do so, we need to have accurate dimensions of both the building itself, but also features on it, like windows and doors and other things. To do so, a viable approach would be to use a laser scanner to capture the point cloud, because doing hand measurements, especially on tall buildings, is not practical. Once you capture this point cloud, then convert that into a CAD model, which will then lead us to shop drawings. But the truth of the matter is that most of the buildings that are in need of retrofit are not straight. They're not Manhattan 90-degree true level prom pristine. They're old, and so they're crooked, and they're buckled, and they're warped, and they have non-planar surfaces. This caricature here shows you what we're dealing with. So to deal with these non-idealities, therefore, if you apply regular software like Autodesk Revit or perhaps even AutoCAD, you will not be able to capture these non-idealities. So over the last 3 or 4 years, under the sponsorship of Department of Energy, Signetron has been developing a scan to BIM conversion tool that takes these non-idealities into account, and we call the tool PADER. So just to give you an idea of the kinds of output that PADER produces, we've been very deliberate in producing outputs that are industry formats that are available to everyone to use. So the first output we generate is the DXF or DWG file, for those of you who are in this business. So that is a wireframe model, and this, for example, in this picture, you see the wireframe model in DXF, which shows a 2-story dormitory building in Syracuse University in New York. So a project that we've been working on. So these are the doors, and these are the windows, etc. So note that even though these lines here look straight and they look like one gigantic line, you'll see in the coming slides that there are curved lines. They're multi-segment, piecewise lines here that connect the things together. More on that later. In addition to a wireframe model, PADER produces what we call a mesh model. So what you see here is each surface in this building has been triangulated with a mesh, resulting in what we call an OBJ file, which is again an industry standard file you can open with Rhino or any other software. But as you can see, there's colors associated with it, and so these colors delineate the non-planarity of each of the surfaces of the building. So, for example, here the red shows that there's something sticking out, and dark blue shows that it's the opposite. It's indented inwards. So why is this important? Well, it's important because if you're recladding a building, you need to have an idea of the topology of the building in order to decide how you're going to shim the panels and how to take into account the non-planarity of the surfaces that you're recladding. So these are the two output products we produce. One is a wireframe model in DXF or DWG, and the other one is a triangulated mesh in terms of a OBJ file. So here's an example of for short buildings or not so tall buildings, like 2-story buildings. People can still do hand measurements, but when you have a 6-story building like this is a building in New York City, it's very hard to measure every dimension by hand. So here's an example of a 6-story building in New York City that we have the mesh model. As you can see, there's non-uniformities all over. And here's the wireframe model for that same building with doors and windows delineated. But here's what I mean by saying that we're taking into account non-idealities of this building. This building is very crooked. It's very, it doesn't have straight edges. So when we're all done with modeling it, this is the CAD model. This is the wireframe model. You can see that it has quite a bit of indentation as it goes from here to here. And similarly, if you look at the same thing in the mesh model, you can see that the building does that. And in fact, those are real. They're not. They are actually in the building. And when you're trying to capture as-built conditions, all of these non-idealities, the warped edges and everything, need to be modeled. So to deal with that, we've come up with kind of like a 3-stage approach. So the first stage is we kind of just model. The easiest thing is to model everything as a planar polygon. So in this case, our polygon is just a rectangle. All 4 vertices are in the same plane, and the vertices are connected with a straight line. So that's the simplest, most naive way of modeling things. And as I've been alluding to it, this is not going to cut it. So what we do, we do corner refinement on this, where we take the 4 corners of this and we move it to match the point cloud. And now we have a warped quadrilateral. Don't worry if you don't understand that term, it's just a math term. But the point is that once we move the corners up and down, they're still connected by a straight line, but they're not all in the same plane. They're non-planar. So that brings us one step closer to the reality of what the building looks like. And finally, then the last step, we get yet and more closer to the reality, and that is we not only are the vertices not in a plane, but the connection between them is no longer a straight line. It's like a curve. And so I'm exaggerating here, showing these curves connecting the edges, the corners of the building. So we've implemented all of what I just talked about in our software. And that is what can result in a system that has these wiggly looking edges and has models the non-idealities of the building. In addition, what we found is delineating fenestrations accurately is very important. And in many buildings, such as the one here, the frame of the window is almost the same color as the frame of the background, like the stucco. It's very hard to know where the window ends and when the stucco begins. So we've developed geometric analysis tools to not just look at the color of the point cloud to do that, but to look at the 3D geometries to help the user visualize those 3D geometries in order to delineate the windows and fenestrations much more accurately. Another feature of PADER is automatic panel layout configuration. So this is the same kind of like 6-story building we were talking about, and in our paneling tool, you can play a lot of what I call what-if games. So if the user specifies minimum and maximum panel width and panel height, these are these 4 parameters in the corner. And then you also specify window to panel tolerance. In other words, how close you want the seam of your panel to be close to the window. Then you kind of hit the go button, and in a matter of a few seconds, our software comes up with this paneling scheme that satisfies these conditions. In other words, make sure that, in this example, the panels are delineated by these green lines. It makes sure that the panels are the width and the height of the panels are satisfied the minimum and maximum condition, and that the tolerance, the distance between the edge of the panel and the windows are all satisfied. So this is a nice tool for architects to use because, especially for very large or tall buildings, because even though aesthetically it might not be as nice as if a human did it, but we can quickly play a lot of what-if games and see what the appearance of these will take like, because each iteration only takes 5 seconds to run. So in this example, we play some of those what-if games. So we start with maximum height and maximum width of 8 feet for panels for this other building, and we get the total of 31 panels. If you reduce the maximum height and width to 11.5, you get 20 panels. sorry, if you increase it to 11.5, you get fewer panels, as you would expect. And you can see these green lines or the delineation of the panel. So you have more panels up here and fewer here. So if you look at zoom into the red area, here we had 3, here now we have just 2, for example. And then further, if you increase it to minimum maximum panel width to 16 feet, you get just 13. So this is what I mean by allows you to play different scenarios, and all of these was generated in less than 1 minute. So it's a very effective tool to do that. So some of the things that everybody has been wondering about is how accurate is the final CAD model we produce. Of course, the accuracy of it as it compares to hand measurements in reality has to do with how well the laser scan was captured, how well the different scans were registered, but also the component that we've been focusing on. Once you create a point cloud, how well you convert that point cloud into CAD models. So this table shows 3 columns. It's a little bit confusing, but I'll try to explain it real quickly. So for this small building in Syracuse, New York, we did hand measurements to measure a certain sort of dimensions. And these dimensions are like window horizontal dimensions, window vertical dimensions, horizontal distance between those, horizontal distance between windows and wall edge, on and on and on. So different measurements. So we did hand measurements. We also use Pader, our software, to create dimensions for those. And finally, we went to the point cloud and inside the Autodesk tool called Recap, and by hand meticulously measured dimensions in Recap. And we repeated the Recap measurements 3 times to make sure that the answers we get are all in agreements with each other before we jotted it down. And these numbers here show the average difference between, for example, hand measurements versus Pader, Recap versus Pader, and Recap versus hand measurements. And the summary or the averages over everything is shown down here. And what you notice is that Recap and Pader are very much in agreement with each other. They're off on average by 0.007 feet. But Recap and hand measurements are off 0.013, and hand measurements and Pader are off by 0.012. And what this is indicating is that really the digital methods of converting to point cloud and doing CAD analysis and even measuring in point cloud, which is an impossible task. It's not practical. You can't be using Recap for your design. But it shows that those two are very much more in agreement with each other. And the other thing is that the average error is very, very small. It's of the order of 3 or 4 millimeters, if you will. If you convert this feet to millimeters, about 3 or 4 millimeters. And some of you might be interested, so this slide shows what we call absolute error, and some of you might be interested in relative error, and the same story is shown here, but now we're just talking about ratios. We're talking about the ratio of the difference between 2 measurements divided by the dimension itself. So that's what I mean by ratio. And so the theory is that some panel manufacturers would like to have this ratio to be below a certain threshold. So that means that you have a larger error budget for longer dimensions than for smaller dimensions. And again, the same story holds true. Recap and Pader are very much in agreement with each other. The percentage off is 0.145%. That means it's 0.00145 as a ratio. And then as soon as you introduce hand measurements, the number becomes bigger, again indicating that really hand measurements are less accurate than either Recap or Pader. Okay, so what are some bottlenecks in these kind of systems? So going back to the New York City building here, one of the challenges we had was that all these buildings have ledges that are sticking out that occlude what's just above them. So there's always a hole or a shadow artifact right above the windows. And actually this effect gets to be worse and worse as you go higher up in the building. So this is a 6-story building. You see it worse at the 6th floor than you see it on the 1st floor. And of course, one of the things people do is they put a laser scanner like on top. But that still doesn't fix the problem that you have missing point clouds. So one of the things we've been looking into is using a climbing robot to climb off a building where we attach a laser scanner to the bottom of it in order to capture those holes or shadows or occlusions. And the fact that these occlusions occur above buildings and fenestrations is particularly unfortunate and needs to be addressed because the fenestrations are very important in your panel design. And it's just exactly the one place you don't want to have errors or missing points or holes or ghosts or shadows or all of that. But yet, with the traditional scanning schemes, that is where there's a lot of missing points. So we're working on developing these scanning robots that kind of like climb up the building and scan those parts and then register that back with the tripod scanning that we do with the terrestrial laser scan on the ground. I also wanted to spend a few minutes to talk about other robotics projects that Signetron has been involved in the last 2 years. So Signetron won both the phase 1 and phase 2 of the DOE e-robot competition in 2021 and 2022. And as part of that competition, we designed robots that would go into attics to both vacuum clean and air seal attics. So I'm just going to show a highlight of those. Let's see. Why can I? Okay. I'm going to fast forward. Stop this. So another aspect of this project was to design a different kind of robot. This is a hexapod robot that has attached to a one component foam here through this long 30-foot cube, and it has some sensors on it, and it uses that in order to air that gives you an idea. Also, as part of this e-robot project, we developed a mechanism using drones with thermal cameras in order to compare pre and post retrofit of a building. And so this is a trailer by DOE in New Mexico. We simply took our drone and took pictures of it. And this data product that you see is using our software to stitch those pictures, not only the RGB pictures to create this panorama. So this is not a picture that we took. It's a synthesis of a bunch of pictures stitched together. But also, as the way this system works is if you click on a particular point, let's say here on the building, it shows you the thermal image associated with that. And so this trailer, you can insert and remove insulation at will. So this shows the picture when insulation was removed from, this is the spot we're looking at here. When the insulation was removed, you can see these thermal gaps. And then we did a second flight, and this time with insulation back in, and you see that this is the picture that you get. So this demonstrates the point that you can use drone thermography, like we've shown here, together with these nice software tools in order to click on any point here and show before and after. And this is particularly useful because when you retrofit buildings, you actually change a lot of things at the same time. You not only do envelope retrofit, you might be doing mechanical system envelope like air conditioning. And so it's very hard to decouple to know and wait for 2 years to look at the utility bills to see if the thing worked or not. But this is a more direct way of knowing whether or not the retrofit you did was good and assess the quality of the retrofit. Did the contractor forget to insulate some parts of the building, for example? And then the last...
Okay, we have about another minute left.
And this is the very last video. Just to give you a bit of a background. So here we've designed a drone with a moisture meter set up right underneath it that's going to fly on tall buildings and measure the moisture level in the exterior of the building. And so as you know, if you have concrete buildings and if there's rain and other effects are affecting its humidity and moisture and degenerating, it is very hard to know. So drones can be used to do that. think this shows the point. I'm going to stop here. Feel free to contact me if you have any questions. I'm also happy to answer any questions now.
Thank you, Avideh. If anyone in the audience has a question, please unmute yourself and feel free to ask.
Ms. Zakhor, how are you? This is Richard Ross.
I'm good. Thank you.
Thank you. Is it possible to get a copy of your presentation?
Yes, I passed it to Sal, but I can also, if you contact me directly, I can also send it to you directly as well.
Okay, fantastic.
And we're
Yes.
recording these so we can make the videos available upon request.
Thank you.
You're welcome.
Hi, this is
any-
Lisa Hart in Syracuse. I have a question. So is it for any size building, regardless of like how many units or how many square feet?
You mean which one of the systems I described? The scan to BIM software?
Yes, would you be able to, like, you can use it on no matter what size, what building, what type of building? Or is it just on certain, like, depending on the facade or the size or square footage?
No, I think conceptually we don't have any limitations on what buildings we can apply it to. We're now working on a 9-story building, so yeah. Did you have a specific kind of building in mind that?
Well, like if you had like an old brick building, like something
yeah,
from
it
like
would
the
be.
1950s, like,
Yeah, this is not that different from this building here. Yeah,
okay,
yeah.
thank you.
You're welcome.
Great. Any other questions? Avideh, I have a question for you. In terms of file sharing and the potential liabilities involved, but also the opportunities for savings so that each trade doesn't have to go to the site directly, pull their own measurements, but actually can share one reliable high-res file. Have you looked into that at all in terms of the potential savings there, but also in the potential risks involved for the reasons I just mentioned?
Yeah, this is a very good question, and the more as time goes on, I'm beginning to realize that in the construction business, everybody is very concerned about limiting the risks and liabilities they have. So figuring out one entity. So at the end of the day, I think that the biggest, I guess, risk here is to have the wrong dimensions and then have the panels not fit the building. And so a lot of times in today's pipelines, the panel fabricator and installer, which are usually the same people, are the ones that kind of like assume that liability of saying, because we lose the most if the dimensions are inaccurate, we want to make sure they're accurate. And so the key point is try to convince them to adopt something like this. And I've kind of feel a bit like a broken record, but I repeat what I've been saying for the last 2 years, which is I think what we have to do is build trust by keep modeling buildings and then keep doing hand measurements. Even though I showed you hand measurements and comparison with hand measurements for just one building, which is this one in Syracuse, we've actually done it multiple times. We've done it for a couple of buildings in Southern California. We've done it for 2 other buildings in Syracuse. We've done it even for this tall building in New York, the 6-story building in New York. So the idea is that as time goes on, and if repeatedly we see the software producing answers that are as accurate or more accurate than the hand measurements, you kind of build a trust that way. But whether or not who at the end, there's only one party that assumes liability, and it seems to me that it's kind of like converging to panel fabricators / installer. So those are the guys we have to convince that the software is good and accurate. Did I answer your question?
Yes, thank you. Any other questions from the audience? I'll ask you one last question then, to your last point. In terms of the tolerances required by panel manufacturers and overclad systems, I understand they need to be accurate within fractions of inches. What is the tolerance level that you're seeing in their production methods, and what are you able to achieve with your system?
So their production methods is really hand measurements, but so and what they have realized is that even though they've been using hand measurements for years, doing a 6-story or 10-story building with hand measurements is just prohibitively expensive. So what we've heard so far is that the tolerance level of having smaller than 0.2% relative error is what they can live with. And so they also agree with us that if you go to recap and do the measurements and repeat that 4 times and make sure you get the same measurement over and over again, then that is pretty accurate. So it's generally agreed upon that multiple measurements in recap is accurate, but that's not practical, because if you try to do that, it's not practical, and it's not also not repeatable. Like if you want to get 4 consistent measurement with recap, you have to try it at least 10 or 20 times to get it. Each time you get a different number. Anyway, so the general, at least for one panel manufacturer, the general kind of understanding is that if you're below 0.2% relative error, that should work with their system. And our number is lower than that, and it's 0.145. So yeah, they trust hand measurements, but they're beginning to realize that hand measurements is only going to go so far, especially if you have big buildings.
Great, thank you, Avideh. Any last questions from our audience? All right, well, thank you so much for attending. Avideh, thank you for presenting, and yeah, look forward to hearing more as this progresses.
Thank you very much for inviting me. And feel free to contact me at this email if you have any more questions.
Great, thank you.